Okay, so let's talk about salts and more practice on determining if a salt is acidic, basic, or neutral. So I'm just going to write down a few salts and then we will determine if they're acidic, basic, or neutral. So first we'll talk about lithium fluoride, and then we'll do sodium bromide, and then sodium acetate, and then ammonium chloride, and then lastly ammonium fluoride. Okay, so all of these are salts, and we are going to determine, is this salt acidic, basic, or neutral? So these are 5 different examples that we're going to look at individually. So, like we said before, the way that we determine if a salt is acidic, basic, or neutral is we look at the ions that these salts are made up of. Remember, a salt is just an ionic compound. We're going to look at the ions that these compounds are going to break up into, and then we're going to see, are those ions acidic, basic, or neutral? And the way we determine if the ions are acidic, basic, or neutral is we see what their conjugates were. So if the conjugate was a strong acid or a strong base, that makes that ion neutral. If the conjugate was a weak acid or a weak base, that makes that ion weak. So I'm just going to go ahead and write that out, and then we will refer to it as we're kind of looking at each of these examples. So the conjugate acid of a strong base is neutral, meaning it will not affect the pH. The conjugate base of a strong acid is neutral, meaning it will not affect the pH. The conjugate acid of a weak base is a weak acid. So it's a weak acid, that means it will affect the pH, that means it will decrease the pH, it will make it more acidic. The conjugate base of a weak acid is a weak base. So weak base, that means it will affect the pH, it will increase the pH. Remember, you are responsible for the 6 strong acids and the 7 strong bases. Anything that is not on this list of the 6 strong acids and the 7 strong bases are considered weak. So you need to know this. You need to have these memorized. You do not need to have all of the weak acids and the weak bases memorized. There are hundreds. And all you need to know is what these strong acids and bases are, and then everything else that's not on this list you can assume is weak. Remember what strong and weak mean. Strong means complete ionization. Weak means partial ionization. These strong acids and bases, their conjugates are going to be neutral. Weak acids and bases, their conjugates are going to be the opposite. So the conjugate of a weak acid would be a weak base. So we're going to use all these examples to illustrate all of this. So let's look at lithium fluoride first. So the first thing that we want to do is we want to break lithium fluoride up into the ions that it's made of. So lithium fluoride is made up of the lithium ion and the fluoride ion. So we want to know, are these ions acidic, basic, or neutral? And the way that we determine that is seeing what they came from. Lithium, as a positively charged ion, is going to be the conjugate acid of a base. So what base did lithium ion come from? Lithium hydroxide. The fluoride ion, as an anion, negatively charged, is going to be the conjugate base of an acid. So what acid did the fluoride ion come from? hydrofluoric acid or hydrogen fluoride. So now what we're doing is we're seeing what effect are these ions going to have on the solution based on what the conjugates were. Lithium hydroxide is on the list of strong bases. So that tells you that the lithium ion is neutral. The lithium ion is neutral because it's the conjugate acid of a strong base. So when you put lithium fluoride into water, the lithium ions and the fluoride ions will separate. The lithium ions will not affect the pH of that solution because lithium is a neutral ion because it is the conjugate of a strong base, lithium hydroxide. So now let's look at the fluoride ion. So the fluoride ion is the conjugate base of the acid hydrofluoric acid. Now, hydrofluoric acid is not a strong acid. It is not on this list of strong acids. Even though fluorine is the most electronegative element, and electronegativity has to do with determining strengths of acids, because of its size, the fluorine atom, hydrofluoric acid exists in equilibrium. It is a weak acid. All you need to know is that HF is not on this list of strong acids, which means HF is a weak acid. If HF, hydrofluoric acid, is a weak acid, that means the fluoride ion is basic. It's basic because it's the conjugate base of a weak acid. So if I ask you if lithium fluoride is acidic, basic, or neutral, you would look at the lithium ion and the fluoride ion, determine that the lithium ion is neutral, the fluoride ion is basic, which means lithium fluoride is a basic salt. Lithium fluoride is a basic salt because when you put it in water and the lithium and the fluoride ionize, the fluorine ion acts like a base because it's the conjugate base of a weak acid, meaning it will act like a base. Okay, so let's look at another one. Let's look at sodium bromide. Sodium bromide, the first thing we're going to do is break it apart into its ions. So the sodium, Na+, is going to be the conjugate acid of a base, sodium hydroxide. The bromide ion is going to be the conjugate base of an acid. So really, the only reason we do this step is to see if this ion is going to act like an acid, base, or neutral. These are not really important in terms of the salt. We just do this part to determine if these ions are going to act like acids or bases or if they'll be neutral. So, because the sodium ion is the conjugate acid of a strong base, so look, here is sodium hydroxide on my list of strong bases, that means sodium hydroxide is neutral. It is neutral because it is the conjugate acid of a strong base. So now let's look at bromine. Because the bromide ion is the conjugate the conjugate base of a strong acid, hydrobromic acid, that means this bromide ion must also be neutral. It's neutral because it is the conjugate base of a strong acid. So that means when you put sodium bromide into water and the sodium and the bromine, sodium ion and the bromide ion ionize, this is a neutral salt. It's a neutral salt because neither of these ions affect the pH. They both are neutral. So let's look at the next one. The next one, sodium ion. And then this is called the acetate ion. You do not need to know that. You just need to know the strong acids and the strong bases. So here is the sodium ion. We just did this before, so we know that sodium comes from sodium hydroxide. We know that because sodium hydroxide is a strong base, the conjugate acid of a strong base is neutral. So I know that sodium ion is neutral. So now let's look at this acetate ion. So you don't need to know anything about this. The acid that it would have come from is acetic acid, but you don't need to know that. You do not need to be looking up these formulas or the names. You just need to know that this, whatever the acid, remember the acidic proton goes out in the front, so it would be HC2H3O2. That's an H, not an A. This is not one of the 6 strong acids. You don't need to know what it is. You just need to know it's not on this list. So that means that this ion, because this is a weak acid, this is going to act like a base. This acetate ion is basic because it is the conjugate base of a weak acid. And again, don't get overwhelmed or confused by some of these bigger molecular formulas that maybe you've never seen or heard of before. It's not important. Just like when we were doing all of the equilibrium tables with acid and base ionizations, you don't need to worry about the specific formulas for now. You just need to be able to identify them as acidic or basic. And again, you know that this is basic because it's the conjugate of this acid, and this acid is not on the list of the 6 strong acids, so that means it's a weak acid, so that makes this conjugate base basic. So that means that this sodium acetate is a basic salt. Okay, let's look at another one. Here we have ammonium chloride. Okay, so here we have the ammonium ion. And here we have the chloride ion. Okay, so the ammonium ion, this is a little bit tricky because it doesn't really follow the convention of the way that we usually write bases, where we usually just add an OH at the end. The ammonium ion is actually the conjugate acid of ammonia, NH3. Ammonia is a base. It is a weak base because ammonia, NH3, nitrogen trihydride, ammonia is its common name, is not on this list of strong bases, which means ammonia is a weak base. So that means if ammonia is a weak base, then ammonium, this is the ammonium ion, this is ammonia. The ammonium ion is acidic because it is the conjugate acid of a weak base. So that makes the ammonium ion acidic. Chlorine is the conjugate base of hydrochloric acid. Hydrochloric acid is on the list of strong acids, which makes this chloride ion neutral because it is the conjugate base of a strong acid. So that makes ammonium chloride an acidic salt. It's an acidic salt because the ammonium ion acts like an acid because it is the conjugate of a weak base. The chloride ion is neutral because it is the conjugate of a strong acid. Okay, one more. Let's look at ammonium fluoride. So, ammonium, NH4+, we said this is the conjugate acid of the weak base ammonia. So that makes NH4 plus acidic. We know why, because it's the conjugate acid of a weak base. Now let's look at the fluoride ion. The fluoride ion comes from the weak acid, hydrofluoric acid, which makes it basic. The fluoride ion is basic because it is the conjugate of a weak acid. So what happens if you have a salt that when it ionizes, it breaks apart into both an acidic portion and a basic portion? What happens? Well, when you have a situation like this, to determine if the salt is acidic or basic, when it's composed of an acidic cation and a basic anion, we compare the Ka of the acidic part, NH4, to the Kb of the basic part, F-. Whichever one is bigger will determine if it is an acidic or basic salt. I'm going to write all of that out, and I'm just going to kind of write it right here. So, to determine if a salt is acidic or basic, when it is composed of an acidic cation, ammonium in this place, and a basic anion, the fluoride ion in this case, we compare the Ka of the weak acid, NH4, ammonium, to the Kb of fluoride. If the Ka is greater than the Kb, if the weak acid ionization is greater than the weak base ionization, then it would be an acidic salt. If the Kb is greater than the Ka, then it would be a basic salt. So you would be provided these Kas and Kbs, or you could always look them up. So the Ka of ammonium is let's see, the Ka of ammonium is 5.6 times 10 to the negative 10th. The Kb of the fluoride ion is 1.5 times 10 to the negative 11th. So what you would do is determine which of these two numbers is bigger. Well, they both are very small numbers, but this is a bigger number than this. 10 to the negative 10th is bigger than 10 to the negative 11th. This is bigger. The Ka is bigger than the Kb. So that means ammonium fluoride is ultimately an acidic salt. Even though it's made up of an acidic portion and a basic portion, the acidic portion will ultimately win out because its Ka is bigger than this Kb. This is something that you would have to determine in a case-by-case basis, comparing the Ka of the acidic portion to the Kb of the basic portion. So these are some good examples, kind of what I would expect you to be able to do to determine if a salt is acidic, basic, or neutral. You do this by breaking apart the salt into its ions, determining if that ion is going to be acidic or basic, and then ultimately how that is going to affect the pH of the solution.